security environment. It could be telephone conversations from many different people, and perhaps you want to track some criminal, somebody, and you have several recordings. In either of those cases, perhaps you will have conversations, so you have several of these speakers, and you want to do some kind of diarization across files. So perhaps you will want to do first diarization in the file, so you label them like that with colors, you do the same thing here, but then maybe later realize that the blue one here is the same as the blue one there, and then you can put this information together. And then maybe another quite popular application of diarization is in connection with transcription. So you want to not only recognize the speech, but assign the speaker labels. So in that case, you will be answering who said what. And here in this GIF, as example, actually I'm touching a bit on one extra thing, which is kind of the mode for diarization. This happens for many tasks, that you can have the batch or offline way of doing things, or streaming or online, where you process and you give, like, you produce outputs as you receive the input. So here, for example, well, you see like the red line shows us kind of real time how speech is spoken, and then we get the outputs accordingly. But the other approach is, well, you have the whole recording and you just process it all at once. Both of them are valid, and depending on the type of application, you might be interested on one or the other. For the rest of the presentation, I will be mainly focusing on the offline or batch application. There are certain things that if you want to do streaming diarization, you will need to take into account, but I will not be touching on those today. All right, and so that's kind of in connection with the different applications, but then you have the domain where you want to apply it. And yeah, there are many things, usually in connection with other tasks like transcription, producing minutes for meetings. So you have meetings, it can be telephone conversations, and this is kind of nowadays very important with call centers, right? Maybe you want to process all that information, and well, diarization is key in that. Nowadays, it's becoming more and more common to have these kind of clinical interviews in a healthcare scenario, but you could have also things like public institutions like parliaments. You have several speakers over several hours, and you would like to diarize that to keep track of what's going on in the sessions. So that's kind of a motivation. And by the way, I didn't mention it so far, but if you have any questions at any point, just raise your hand. I think I tend to look at the crowd all the time, so I will spot you. So feel free to interrupt, not to have parallel conversations because that becomes annoying for the presenter, but questions, welcome to answer them. All right, I guess no questions so far.
Yes, I have a question. These different voices, how do you distinguish each voice from each other?
Okay, so for the recording, like, the question is, how do we recognize the different voices? How can we tell them apart, right? So we will get that into a few slides when we start describing the technology. Okay. Also, I will try to police myself to repeat the questions, because otherwise in the recordings you cannot hear them, but if not, just let me know if I forget. Okay, and why is this difficult? What are the challenges in diarization? Well, first of all, and here I'm focusing on the most general way, if we can say that, focus on the most general scenario. Basically, you don't know a priori how many speakers there will be. So that's one of the problems. You have to kind of classify your speech, but you don't know how many classes there will be. And of course, they are different from one recording to another. So you just want to tell them apart. There is also the fact that in conversations, like natural conversations, you will have some segments that are very long and some segments that are very short. And you want to handle all of them equally, especially if you think of conversations. Let's say there is somebody speaking, and there are what we call here back channels, which is, for example, when somebody says, right? Or these kind of things that are very, very short, probably less than a second, and you still need to catch them. And for certain cases, those are very important because they convey that somebody is agreeing to something. So if you want to do minutes for meetings, you need to capture these kind of things. And those are very hard because they are very short, so finding that somebody said something in a very short lapse of time, that's tough, and usually they happen on top of other speakers. So somebody's speaking, and then you say on top of each other. So that's the overlap speech, which is currently one of the main challenges of diarization. Then you have also the fact that not every speaker speaks the same amount of time. Some of them perhaps, let's say in a meeting, tend to take more than 50% of the time, and some other maybe speak very little, and you still want to capture those. So that's something that you need to take into account and evaluate your models accordingly. Then, as with many other tasks, the acoustic scenarios can be very different. And this is also something that has been evolving over the past few years, because now we have many more ways of recording, like recording devices, like cell phones can record very high quality audio, which 20 years ago was not the case. Maybe you would have telephone conversations, maybe some meeting if you were rich enough to have some far-field microphone to record your meeting, right? These kind of things. Nowadays it's much more common, so it's much more common to have recordings, and then you want to, there are many more technologies that you can develop, and you want to enable certain scenarios with diarization. So that's important. And the last one here, which is maybe still important, is the precision that you want to have in your outputs. So we said, who spoke when? Well, you want to mark the speech segments. Even among humans, it's not so easy to agree on the specific boundary. If two of us listen to the same recording and we want to annotate it, well, probably we'll have some differences there. And what's enough? Millisecond precision? We will not agree on millisecond. Well, but we want our system to be precise enough. Maybe not millisecond, but 1 second is probably 2 cores. We don't want to have that. So this is something that eventually for a practical application you want to take into account and be sure that you are handling those situations well. So related to these kind of things is the measurement of performance. So we have here on top the reference annotations. So that's something that, let's say, our gold standard, a human annotated that. So when we want to evaluate our model, we want to check, okay, is this good enough? So the good enough will be that manual annotation. Our system will produce some kind of output, and it can have mistakes. Like systems will make mistakes here and there. The metric we normally use, we have been using for quite some time, since it was proposed like more than 20 years ago, I guess. NIST in the early 2000s started with like the definition of diarization and also proposed the diarization error rate. Diarization error rate counts 3 different kinds of errors. So you have the missed speech, the false alarm, and the confusion. So let's get into examples of each one of those. So we have, for example, here miss, because the reference says there was speech from one speaker, but our system said that there was silence, so it's missing that. So we will account for this lapse of time. Here there is another example, because there should have been 2 speakers active over there, but our system said, well, there was only 1, so we are missing that as well. False alarm is the opposite scenario. So here, for example, it says there is speech where there shouldn't have been, or here it finds 2 speakers active, but there was just 1. And then we have the last one, for which actually it makes sense to first discuss something that I'm kind of omitting so far, which is the colors here denote a mapping between labels. So I commented before that we don't care about the specific identities, right? So our system is good saying speaker 1 and speaker 2, that's okay. But we need to know who is speaker 1 between Alice, Bob, and Carol, and who is speaker 2. So the way this is done is you consider the different mappings. So speaker 1 can be Alice, or Bob, or Carol, and then you have all the other speakers being assigned to the other identities. So you have many different mappings. Out of all those, there will be one with the lowest error. And that will be the one that you consider, because any of the permutations are equivalent for us.
So,
yeah.
So what you're saying is that if we had mapped speaker 2 to Carol, then what's being called a confusion would be correct.
I will get to that in a second, yeah, sorry. I will not repeat it because, yeah, I will get to that in a second. But basically, we will pick the one that has the lowest error. And that leads maybe to the last type of error, which is this confusion. So here, I'm saying, well, this is confusion over here. But that's because I chose speaker 2 mapped with Bob. I could have chosen speaker 2 mapped with Carol, right? That's a valid option. So if I did that, actually, given that this segment over here is longer than this one over here, well, mapping speaker 2 with Carol would tell, this is fine, but then here you would have confusion. And since this is longer than this one over here, actually it's better to map speaker 2 with Bob. We don't get penalized here, that's okay, and then the confusion is only this part with Carol. Any more comments? No, good, all right. So basically we will sum all these segments of miss, false alarm, and confusion, and then we will normalize by the total amount of speech. So we will sum all the segments that we have there in the reference, and usually we will present these in terms of percentages. So that's the usual way with diarization rate. And there is one thing here, which is, well, we are normalizing by the total amount of speech, which means that actually DER can be higher than 100%, because if you have lots of false alarm, that will increase a lot your sum of error and eventually get to more than 100. Yeah, that will not be a very good system in that particular file or scenario, but that can happen, and you need to think of it eventually when you analyze the errors. And eventually, for a given system, it makes sense to analyze the different errors that you have, the miss, false alarm, and confusion. There are other metrics. This is not the only one, but it's the main one. So that's why I'm bringing it up. There will be later some results that will be in terms of DER. I will not be talking much more about this. There are other things like forgiveness color, which means around each segment, I have some tolerance for errors that I could make. I will not be talking more about that, but 2 years ago in JSALT, Bredan, he had a diarization presentation, and he discussed about the metrics quite a lot. So my recommendation is, if you want to learn more about this part, I will be focusing on other things, but if you want to spend more time on that, I recommend that you check that. The video is there public, so in 2023, you can just search it, and it will be quite nice addition to this. All right. So the main core of the presentation is more about, well, the different ways of doing diarization and kind of this historic perspective of how things have been changing. So as I mentioned a couple of minutes ago, diarization as the task that we know nowadays has been proposed about the year 2000 or 2002, something like that. NIST came up with kind of a formal definition, protocols for evaluation, including DER, like how you, basically when you set up a task, you have different things to take into account. Well, the definition, kind of formal definition, what it means to do a certain task, how you evaluate it, but probably also you want to have some data so that you can evaluate your models and know, well, compare technology and that way push it further and improve. So around the year 2000, they came up with it, and for a very long time, all the systems for diarization were what we call nowadays modular systems. We'll see in the next slide what exactly it means, but you can imagine different parts, and each one takes care of a different part of the problem, and then when you put them together in a sequence, you get the full diarization output. But a few years ago, end-to-end models, and by that we mean a single neural network that will handle everything, takes care of the task. And so you give speech, and you get the labels, which is what you want. And more recently, there started to be some hybrid systems which combine things from modular and end-to-end systems. So we will get to that a bit later in the presentation. So let's start with modular systems. Modular, sometimes called cascaded also, because you kind of have one step after the other. This was the traditional way of doing diarization. As you see, there can be many different steps. I mark here kind of the main ones. Those are the ones that you really need if you want to do diarization. And perhaps you can consider the other ones as optional in the way that literature has been developed. So all these different steps have some kind of feature extraction. So you saw in the last couple of days that the guys were talking about different speech-related tasks. Well, speech is a signal. If we digitalize it, you have some kind of sequence of numbers. You have some encoding, some sampling rates, so you can interpret it and process it. But we don't take that normally. We would extract some features, like acoustic features. You've heard perhaps about MFCCs, filter banks. Perhaps you are already working with them. But basically, there is some level of feature extraction in all these guys. It can be the same features. It can be different. Like some of these steps can even run in parallel. So you might actually have completely different pipelines for each of them. But the common pipeline for diarization is just this one. So let's go a bit over the different steps and what has been done related to each one. So we have this very first step of signal preprocessing, where we want to just improve the quality of the signal. So options for this have been denoising, reduce some background noises, reverberation, especially in a big room, you might have quite a lot of it, or more in general, enhancement of the signal. Also, it might be that you have several channels because you have a meeting room set up with some microphone that has a microphone array, so you have several microphones. You can do some kind of enhancement using all these, but maybe just pass one single channel for everything else, because that makes it cheaper. That could be one way, or because you don't have a good enough technology to take advantage of the multi-channels. But that could be another type of preprocessing. A key step is also voice activity detection that can be done as easily as using something energy-based. So you just measure the level of energy. If it's above a certain threshold, you say, this is speech. If not, this is silence. That works if you have very quiet environments, no background noise, no reverberation, and so on. As you start to get to more tricky situations, that will probably not be so good, even though it's very lightweight and easy to run. Throughout the time, GMMs with hidden Markov models have been quite explored in this direction. But nowadays, and from already a few years ago, neural networks is what dominates the scene in terms of voice activity detection. And it's important because once you have the speech segments defined, you will now move to the next step, which is segmentation. So in the way this historically developed, you would first run voice activity detection. Now you get a very long segment because there was just speech, but it could be that here there were many speakers taking turns. It was just kind of continuous. In a conversation, let's say, with a friend, maybe even a coworker that you have a very good relationship with, you tend to interrupt each other very quickly, and there are no silences, so you have very long segment, maybe 1 minute, but segments in there that correspond to different speakers. So speaker change detection was the technology of finding where there are the breaks, the changes in between one speaker and the other in that speech segment. But with the technologies related to speaker embeddings that Olga was describing yesterday, actually it made also sense to consider uniform segmentation. So for example, every quarter of a second, I get a new speaker embedding that I will use later for clustering and whatnot. But that means, well, I don't need to care about speaker change detection. I just get my speech segment and take little segments every quarter of a second. That's perhaps good granularity for certain cases, and that's good enough. So that's another approach. And then there is here this ASR-based that I added at the end. In the last few years, there have been some models that that produce transcription, but also including a speaker change token. So you get all the tokens of a speaker, and then it marks there is a change here, so a different speaker will start, and then you get the other one. So that could also define this. But we will touch on this towards the end, so this is maybe not so historical perspective, but more of a recent trend. And this segmentation is eventually important because we need to have some kind of features to do clustering. So you can use just acoustic features like MFCCs. Then eventually when I-vectors came, as Olga was describing yesterday, these generative-based speaker embeddings, that started to be used. And then eventually X-vectors or D-vectors, which are the variants of discriminatively trained speaker embeddings. So you extract them on these segments provided in the previous step, and then you do clustering. For a very long time, and probably until end-to-end models started to appear, most of the diarization works focused on this very part. Not to say that that was the only thing, but what happens is this kind of pipeline takes advantage of other technologies. So whoever builds voice activity detection maybe doesn't do it only for diarization. It can be used for ASR. For transcription, you need it. Maybe also for speaker verification. You use the same model, and you don't need to retrain. So that's pretty good, and you just take it. Regarding the speaker embeddings, that has always been very connected with speaker verification, speaker recognition. So whatever improvements, like it happened with I vectors, then with X vectors, that can be taken for diarization as well. So most of the core happened, or like most of the diarization papers focused on the clustering, how to find the number of speakers, which is one of the challenges, and then assign the segments. So historically, there have been models using Gaussian mixture models. Then agglomerative hierarchical clustering became quite a strong way of clustering speaker embeddings, I vectors, X vectors. So here, basically, what you do is you compare every embedding against each other. You have some notion of how similar they are, and you start clustering. You put together, these two are the closest to each other over my whole set. I put them together. And then you do the same thing with everything, and you cluster until a certain point. Spectral clustering has been also quite popular. And here, the spectral part encodes the notion that you transform the space into something that makes better sense for your clustering, and then k-means takes care usually of the clustering itself. There have been also hidden Markov models where you have states representing speakers, and we also worked quite a lot with the variational Bayesian hidden Markov model. In more recent times, neural network-based approaches for clustering also appear with certain success. So now I will move to the last step, which is this post-processing. So there are several things that can be named post-processing. You can have improving boundaries, because especially when you do this clustering every half a second or every second, because you extract your speaker embeddings without granularity, maybe you want to have some better precision inside that 1 second long segment. So eventually doing some resegmentation there could help. Also, so far, I didn't comment on overlap. None of these other steps really handles overlap, because when you do clustering, you assume that, normally, assume that that embedding represents or corresponds to only one speaker. So you're not doing anything if two of them appear together. So the way of inserting overlap detection here, handling overlap, is by doing overlap detection and then doing some handling of it. So overlap detection has been done with hidden Markov models, but then later with neural networks. And the thing with this is that with any detection problem, you can have voice activity detection, right? You will have certain level of miss, certain level of false alarm when you evaluate your model. Overlap detection is the same. You will also set some threshold, you will have some miss and some false alarm. The problem here is that even in the cases when you detect overlap, that doesn't guarantee that you will assign the correct speaker. You still need to handle that. You found that there is overlap here, but now you need to assign, like, hopefully, your model found speech there. So now you have speech of one speaker after your clustering, but you need to assign a second identity or a second label for that part. So there have been different approaches. The most common heuristic is you take your segment of overlap and you start looking to the left and to the right of that segment and check which is the closest other speaker that I find here. And then you assign that there. That is, of course, quite naive, but it works quite well, especially when you compare it to other approaches. Like even if you take some probabilistic model that will give you probabilities for a given frame, so you get the probability of all the speakers there, and you take the second most probable one, that's actually not that good. And the main reason for this is, well, overlap detection is hard, for starters, in comparison to other tasks, but even once you set your threshold and you find overlap, you might still make a mistake. You might still put a label there which is the wrong one. So it doesn't buy you anything. Like, yeah, you found the overlap. Maybe you did it right, but then you screw it up with the wrong speaker. So even if you have, let's say that the threshold for precision recall is reasonable, that maybe doesn't translate into good, into improvements on diarization. So that's why eventually this way of handling overlap is not so successful. Usually, yeah, we would get some improvement, but kind of marginal in comparison to other things that one could do. And then there is this last option, which is the fusion of models. So in the context of a product that you want to run, this probably doesn't make so much sense because you will need to run several different systems and then fuse that to produce an output. Usually you will want to have something that runs fast and produces a reasonable output. But let's say in an academic context where we are kind of pushing the numbers and trying to get like squeeze the last drop, for example, in a challenge, maybe you have different systems that perform different, like they do different things to perform diarization. They don't work all the same. So each one has advantages, disadvantages, but maybe you can fuse them. With a majority voting, if you have, let's say, 3, well, if 2 of them agree, I pick that label. Or something a bit more, let's say, more difficult, but at the same time more effective, like Dover, which is kind of an extension of Fusion for ASR pattern diarization, or the overlap, where you also handle the overlaps. And this eventually provides gains. So this is the kind of landscape for how modular systems work. Just to show you an example, and this is the VBX recipe that Honza mentioned in the introduction. We had quite some success with a recipe like this a few years ago. And here you can get an idea of the different steps until you get some output. So you start with voice activity detection. As I mentioned, you will get the speech segments. Then we would do uniform segmentation. So you get all these little segments that we would do 1.5 seconds every quarter of a second. So you segment the speech segments. And then we would use X vectors. So back then, we had quite a strong ResNet-based model that, so in 2019, that was a very, very strong results in this voxel speaker recognition challenge. So we use that technology. And then you extract one speaker embedding for each of those little segments. And then you need to do the clustering. So what we did was to use agglomerative hierarchical clustering as an initialization. And that means we wouldn't run it to get the best diarization possible. We just run a few steps, kind of put together some of the embeddings. We would get something, a reasonable starting point for the next step. And the interesting thing here is, well, we didn't need to tune the threshold. Normally, if you want to do diarization with agglomerative clustering, you need to tune your threshold so that you kind of get the best operating point where you join the segments that you want to join, but you don't over-cluster. Here we would just under-cluster, set some low threshold, and that's good enough. And how does that work? Well, here we have an example of this that I was commenting before about, well, you take all your speaker embeddings and you compare them against each other. Nowadays, it's quite popular to use cosine similarities. So you just get an idea of how similar they are that way. There are other options, as Olda was commenting yesterday. You can use a backend, like probabilistic linear discriminant analysis, which is more robust to different acoustic environments. So eventually, it's a good thing here for this type of pipeline that we want to do diarization on many different recordings. So you get all your comparisons, and then you eventually run the merging of these. Right? You put together those that are very close to each other. So you start with these that are very dark, and so on. We get then some kind of clustering like this, where you see, well, these 2 were assigned to the same cluster, these 4 to the same, then 2. So it's not kind of a full, like, well, it could be, but in this case, there are too many. There were not that many speakers in this case. And that's where we would give it to the VBX part of the pipeline, which is we have a hidden Markov model where the states represent speakers. And so each state has a certain distribution. The strong part of this is that the parameters for those distributions are initialized from the PLDA model. So that gives a very, very strong background for those speaker models. And then here there is an iterative process where you would get the probabilities of each of the states producing the embeddings. You would get some assignment of those embeddings to speakers. You would re-estimate the parameters for the distributions of those speakers. Yeah, question?
How do you determine how many states, how many speakers you have?
Right, so the question is, how do you know how many states to start with, right? Well, if you know a priori, you could do that, and you would say, okay, I know that there are 3, so I will just put 3, and then I allow like interactions from any to any. But in the most general way, you don't have that. So the trick here is you would have more than you expect. So an upper bound, it could be 10, it could be 20, maybe it will depend on your application. But in the Bayesian inference, there is a way of eventually dropping some of them. So some of the states are never reached. So the way you estimate the parameters of the model, the probability of, let's say you start with 3, but the probability of getting to state 1 ends up being 0. So it's as if it was not there. So you just end up with 2 of them, and that's enough to assign all the embeddings to the speakers. So, yeah, thanks for the question. So yeah, in this iterative process, you will have assignment of the embeddings to the states, re-estimate the speaker models, and then do the reassignment, and you can iterate this until convergence, and that's basically how the model worked. Right. Maybe just as a segue to the next slide, as we see here, in this pipeline, well, there are many steps, right? And well, you need to run them maybe sequentially, like voice activity detection, and then eventually you get to the clustering at the end. So one thing that we worked on kind of recently, last year, was to have a single model that could give you the speaker embeddings, but also perform voice activity detection and overlap detection. So that basically, for the same, pretty much the same inference time, you would get all these outputs, and then you would use them in a pipeline like this. So you have kind of the encoder, the ResNet, which is the expensive part of the model, is the same. And then you use some linear layers to either produce per frame embeddings. So in this case, we don't use the pooled representation like in speaker verification, or as I was describing before, like 1.5 seconds, I just produce one, but rather you will produce them more frequently. So that gives you better granularity, which is good. And the performance can be quite good, so that's eventually what we found. And at the same time that you produce those regular per frame speaker embeddings, you get these representations that you can classify and say, oh, this is speech, this is not, this is overlap, this is not. And then you get the outputs that you would need for the rest of the pipeline. Basically, now you don't need to extract the embeddings only on the speech part. You just drop the ones that you don't care. And with the overlap, then you assign eventually a second speaker there as well. So this is kind of a way of showing, well, even though modular systems are, I don't know if dying, but they are not so popular nowadays, end-to-end models are much more popular, still there are certain things that one could think of to improve these types of pipelines. So getting to kind of the end of these end-to-end modular systems before we get to end-to-end, just to list what are the advantages and disadvantages of this. One good advantage of modular systems is that you have this kind of plug and play. Like if somebody develops a better VAD, you can just replace the one that you have and use the better one. If somebody gives you better speaker representations, like I vectors to X vectors, that was a huge improvement, not only for speaker verification, but for diarization as well. But if you get now a better speaker embedding extractor, like a better version of X vectors, you can replace it, and that works kind of the same. These type of models, and this is a bit of a spoiler, but they are good with several speakers where end-to-end models are not that great. So they have an advantage here. And we can probably parallelize many of these steps, especially if you have all these speaker embeddings and you need to extract several of them, maybe you can run them all in parallel, and that's pretty good. And one important thing also is that these models can be trained, or like the different modules in the modular system can be trained on cheaper labels. What do I mean by cheaper? Well, we discussed before about annotating for diarization, right? Like you listen to an example and you need to mark the segments. And that's costly. If you want to, for example, annotate 1 minute, probably you will need to listen to it many times. Even for somebody that is trained and they do that quite often, they will need to listen to the example quite a few times. And it's not always, every minute is not the same. A case where you have overlap or you have many speakers interrupting each other, that will be quite tough to annotate, and it will take quite some time, and you need to adjust the boundaries, and all that makes it costly. So we don't really have so many data sets that are not manually annotated, so the amount of labels that we have for diarization are not that large, like the quantity of hours. In contrast, for example, when you train a speaker embedding extractor, you have these labels that are, okay, this recording corresponds to this speaker ID, and that's your label. Olda, yesterday, commented on ways of doing that. Like nowadays, there are these pipelines like, well, speakers in the wild, VoxCeleb, CNCeleb, now I forgot the name, but there is a newer one that is larger, and they follow these kind of semi-supervised or approaches to kind of label that, and basically you just need the recording and somehow assign a speaker identity, but the recording can be very long, and that's kind of, in some way, a cheap label in comparison to this very detailed millisecond, perhaps, precision. Even for transcription, you have this recording, and this is what was said. If you speak the language, maybe you need to listen to it a couple of times, but not so many, and you will get some decent annotation for that, and then maybe you would do force alignment as it used to be before. Nowadays, maybe you don't really need that, and you can still do. For diarization, that's not the case. And what are some of the disadvantages? Well, we commented that this plug and play and reusing technology is good, but at the same time, it's not so good in the sense that now you have each of the modules are trained independently with different objectives, and maybe they are not the best for diarization. Think of voice activity detection for transcription. Probably you are fine being more lenient on the side of wider boundaries. Like you have speech, but maybe you don't want to be super sharp and find it exactly where it starts. Maybe you're okay with adding, I don't know, 100 milliseconds around before and after, because actually that silence can help you in detecting speech. But maybe for diarization, that's not so great. So you have these kind of things. Running the systems is cumbersome.
Do you also have weakly aligned data, such as, let's say, the transcripts, so that you don't know exactly on which millisecond a speaker begins and ends, but you just know that someone spoke and then someone else spoke?
So the question is if we have weakly labeled data, so maybe you don't have the whole segmentation, but you know more or less here some speaker spoke, then there was this other part of the transcription corresponds to another one. I guess in some data sets you would have that, but you wouldn't know exactly where the change is. So you would need to do still something and process it. It's an option. I don't think it's so common, or it hasn't been explored that much. So I was saying that running these models is cumbersome because you have several steps, have to run one after the other, and if one of the steps fails, well, you need to recover, you need to perhaps rerun things, but not only that. If you make a mistake, an error in one of the steps, you will carry that until the end. So that can be an issue, and maybe you have very good clustering, but if you didn't do so good VAD and segmentation, you will be screwed anyway. So, and the last one, which is not a minor thing, is that as the technology evolved, the confusion errors became smaller and smaller, and then overlap detection plus handling became more relevant, and that's something where these models have very large problems with. So I know that maybe some people are kind of falling asleep, so now it's time for a poll. So who knows the movie Die Hard? Who has watched it? Like, it's kind of old, it's even before I was born. So please raise your hands, those that have watched it. Very few. Okay, yeah, not even half. So many of you probably will not get the reference in the next slide, but well. Anyway, I don't recommend you to watch it, but up to you. If you enjoy it. And then the second one, which is controversy in internet, is Die Hard a Christmas movie?
Yes.
Oh, so raise your hands. I mean, you were very emphatic with your yes, but I need hands. It's quantity, not just quality. Is it?
So hands up means yes or no?
Yes, hands up are yes. It's like 5. So yeah, no, I guess no. I guess here we have more of a Popelka kind of crowd. So yeah, not a Christmas movie here. All right, so I was commenting on these modular systems and the problems that are related to them, but I need to put into context Die Hard, which is kind of the, I would put this series of challenges as the turning point between modular and end-to-end systems because it served as the test bed for Diarization. What happened was that over many years, like since the early 2000s until about 2018 when this first Die Hard challenge appeared, the problem was that, well, first, there were only few data sets that you could use for Diarization because, annotating is expensive. We discussed that. So you would have some telephone recordings, you would have some meetings, and that was it. There were not really many public data sets. So that's one issue. The other one is even though Diarization already existed, there were these different forgiveness collar, different ways of evaluating. So I mentioned that the core of Diarization was the clustering part of things. So people focused on that, and that meant they would take Oracle voice activity detection. So they wouldn't do that part. They would just take the speech parts, and then they would ignore the overlaps. So they would just kind of cluster the parts of speech that corresponding only to one speaker. And that was the status quo for quite some time, even until 2018. That was quite common in the publications. And then the first Die Hard challenge appeared, and that's the segue, like the name is Die Hard for the challenge, and in the idea that Diarization is hard, and the data sets that they proposed had many different subsets. So development and evaluation would have about 20 hours each, and then you would have 2 hours of each of 10 different domains with different characteristics. We will get into them in a minute. But basically, this proposed a way of, well, let's evaluate Diarization, and let's not use forgiveness collar, so nothing, like you will trust your annotation as is. But more importantly, for the publications is, well, we will evaluate everything, silence and speech, and also overlaps. So that was kind of the test bed that was set with this series of challenges. So the first one was in 2018, then the second in 2019, and the last one was in 2020. And just for you to get an idea, this was actually quite welcomed by the community back then. So these are all the submissions that happened in the track 1 and track 2. And there were 2 tracks. In all the third editions, track 1 was Oracle voice activity detection, and the track 2 was basically you do full Diarization. And maybe nowadays you think, that's outrageous. How would they have 2 tracks, one that doesn't evaluate your VAD? Well, it used to be in all the publications, that was the case. Like you would separate that, so they would have two different tracks. And you can see that, well, there were many submissions from many labs, I think 10 to 15. So it was quite popular, and then it was also nice that there was a session in Interspeech where everyone gathered. I guess nowadays it's very common with challenges. There are many challenges, I think, over the past years. I don't know if maybe folks that have been around for a longer time, maybe you can compare to 10 years ago if it was that common, but I don't think so. Maybe you would have NIST evaluations and these kind of things that were yearly held. But nowadays there are many challenges with many different tasks. So that's good because it brings the community. You can check the system descriptions of others, discuss them, and so on. So that's quite interesting. And I mentioned that there were different data sets. So these are from the third Die Hard challenge. And so we have here, for all the submissions that were submitted to the challenge, they prepared these box plots. So you have here the overall performance, track 1, track 2. Let's focus only on the track 2 in blue. You can see that, well, there are different, so this is the overall performance, but over here you have all the different types of data sets or characteristics in there. You start from audiobooks where you have a single speaker, so that's kind of easy. Like you don't really need Diarization there, just detect speech or not speech, that's enough. But it's a way of validating, okay, your system is not ruining the good quality it should have on a single speaker. But then you have things like telephone conversations over here. You have court recordings, so you have the jury, and maybe you have several lawyers speaking. You have meetings, which is quite popular, and even restaurant conversations. And just this also serves as the way of setting some reference of what's good or what we should be looking for in DR. And I would say if you are below 10 DR, those are pretty good results. So that's something you can use, and maybe the next steps will not suffer so much. Of course, the lower the better, but if you are below 10, that's probably good. 15, maybe that's acceptable in certain cases, but as you go higher and higher, that will not be that good. And that's, for example, what we see for meetings, which is kind of a popular type of recordings. You see the box plot, even the best result there is at 30 DR. That's incredibly high. These situations are hard because maybe you have a few speakers, 4 or 5. They maybe overlap with each other. They jump into, they barge in, and that makes it quite tough. You have lots of overlap. The models are not perfect. And then you have like this most difficult case, which is this restaurant. You will have the recording of one table, but around you have other tables, other people speaking, lots of noise. So yeah, that becomes quite hard. And as you see, some situations maybe are good enough. I don't know if we could say solved, but many other scenarios are not. So about this time, and actually I had it kind of over here, in 2018 and 19, the winning teams had modular systems. So these systems that we were discussing so far, they reached very good performance. They were the state of the art. But then in 2020, end-to-end models started to appear. And even though there was not a single end-to-end model that would perform great, they did well in scenarios where the modular systems didn't. So for example, if you fused your systems, then you could actually get some improvement, and that worked quite well. So taking kind of the best of both approaches in there. So around that time, 2019, 2020, these modular systems start to hit their limits. So you have very good speaker embeddings. X vectors were already kind of popular. People already kind of stopped even comparing against I vectors back then. And you have also strong clustering methods. So the confusion errors are much lower. Now the overlaps are kind of the, I don't know if last mile, but it became the next hurdle in speaker diarization. Kind of in the meantime, we saw even that voice activity detection, even the speaker embeddings are based on neural networks. So, and this is just to name the ones that are related to this task, but kind of in everything that is machine learning, 2015, neural networks were there. Why not in diarization back in 2015, let's say? Well, there are some particular characteristics in diarization that make it quite complex, not so easy to tackle with neural networks as other tasks, perhaps. One of them is that it's a sequence-to-sequence problem where you need very long context. If you think, for example, for transcription, usually you need some time context, but usually it's kind of short. You want to decode the next token, the next phoneme, the next word, which is kind of a short span. And even for that, for example, recurrent neural networks, which are the ones that could handle long context before transformers. I guess for many of you now, transformers is the bread and butter. You were born with transformers are given. I mean, why wouldn't you use them? But a few years ago, that was not the case. So recurrent neural networks were the way to handle these sequences, but they struggle a lot when you have very long recordings. Think of several minutes where you have inputs that are maybe a few per second, or many if you wanted to use acoustic features, many more. So these recurrent networks wouldn't handle those very long contexts so well. And I was comparing with these like in short spans, maybe it's okay to have recurrent networks, but over several minutes, that will not be the case. You want to know that the speaker here at the beginning is the same as the 10 minutes later appears over there. So handling that is not so easy. And the other thing is you have this multi-label classification. A priori, you don't know how many speakers there will be. So it's like your model does, you don't know how many outputs you will need to be providing like annotations for. So those two things, task itself, somewhat hard to be modeled with neural networks. And then on top of that, we put the low volumes of supervision. So we discussed labels are expensive. And to train neural networks, you need lots of data, much more than for other types of models. So how do you handle that? Well, these were kind of the issues that why not using neural networks for diarization? Well, you need to kind of solve or at least handle these very well. And that happened until about 2019, when the first approach appeared. And maybe for some of you, it feels like a long time ago, 2019, maybe you were even in high school. I really don't know like what to expect from the people here. It's also funny to say this in front of Honza, Lukash, Sanjeev, like, yeah, I mean, you were here even long before, but it's this kind of idea. Many things happen in just, I don't know, a span of 5 years. And nowadays you see, yeah, modular systems. That's, what? Why? Well, this is kind of to explain a bit the evolution of how things develop. And that's how we get now to end-to-end systems. I need to drink a bit because, yeah.
You can also do some break.
There will be, after we cover this, there will be some break. Yeah, I guess, yeah, okay, I'm taking my time. So I will maybe try to be a bit more brief now. But the first way of modeling diarization with end-to-end models was this end-to-end neural speaker diarization with permutation-free objectives. We discussed at the very beginning that for diarization, we don't care about the specific identities. We just want to tell the speakers apart. So different permutations of the labels can be valid. And that's something that you need to take into account when you want to train your model for a general way general way for diarization. You want to have your neural network, you take your speech, you give it to a network, and it gives you, for example, frame activities. So some probability that this speaker was active, I don't know, here very likely, here not so likely, and the same thing for the other speaker. So that's basically what you want to get. But, well, one way is you fix the outputs, and I train, this is the first speaker, this is the second speaker, and I train my model to do that. But now I flip the input, and maybe the model will not work so well. So we need to be invariant to that. And that's why we have these, permutation-free objectives. So what you do is you take your labels, but you take, in this case, that there are two speakers, there are only two permutations. So you take both of them, you calculate binary cross-entropy for each one of them, and then you pick whichever is lower. That's probably the best the model can do at this point. And I will backpropagate the network using that output. So I will train the parameters using that choice. And that's the basic idea of how this happens. Now, there are different ways of doing these laws. So I mentioned this binary cross-entropy, kind of a standard way. The one that has been done for quite some time is having what can be called multi-label encoding. So imagine you have these 3 different speakers. You have the turns, the segments of each one of them. So your labels will be binary. You will have some moments when one of the speakers is active. You will say this is 1. If it is not active, you will say that's 0 for all of them. And that's what you will train your model with. So you train your model, and then at inference time, you will need to set some threshold. So these are your probabilities, the outputs of your model, but you need to decide this will be my segment. So you set some threshold, whatever is up above that threshold will be speech, if not, it will be silence. This works reasonably well, but whenever you have overlaps, it's not uncommon to see that maybe one of the speakers is very nicely detected, and the other one, like the probability rises, but maybe not enough to make it to the threshold. So that causes problem because, well, the model can find it. I can maybe try to lower my threshold, but then I will increase my false alarm. So there is this kind of trade-off, kind of in a detection problem in the same way. but for detecting the activities. So what's what they proposed over here, this power set multi-class cross-entropy. The idea is, instead of modeling that way, you would have one specific class for each kind of scenario for those speakers. So you can see, for example, when there is silence, that will be one class. So it's kind of, that one over there is the same as here, just you have here silence, so here these ones will be active. Now you have here Alice, only Alice is active, so you have this active. If only Bob is active, if only Carol is active, and then you have the overlap between Alice and Bob. So that part is yet a new class. And the same thing you would have for each of the combinations. Eventually, you can do even combinations for 3 speakers, but that's not so common. So eventually, you can probably, like, you are safe enough considering only overlaps between 2 speakers. And proposing this eventually has quite a few advantages, and is becoming more and more popular nowadays. So basically, each of the classes now are modeled independently, so the overlaps have a front seat in the way of the modeling. It's not just given by 2 independent speakers being active. They are also mutually exclusive, and now you don't need to rely on the threshold, because since all the classes are mutually exclusive, you just need to pick whichever has the highest probability, and that will be your output. So that also brings quite a few benefits, especially when handling overlaps. So, yeah. I couldn't even hear you. If I'm taking some input, what? I'm missing the very first part. Yeah, I didn't get the question, that's the thing. If I'm getting better results with the power set loss. So in my experiments, I use this model, the change of loss in the context of a fully end-to-end model. And I was training with many speakers, up to 10. And there, I didn't see any improvements. The thing is, when you have up to 10, the power set for 10 is huge. So I assume that was probably the reason I was not seeing improvements in such case, because yeah, I mean, now it gets kind of diluted. You have too many classes, so in that case, it doesn't help so much. Now, if you are limited to just a few speakers, for example, a fully end-to-end model, but you know that there will be not more than 3 or 4 speakers, then the scenario is different, and I assume there should be some improvement. So you were saying that you spoke with Alexei, the author of this paper, and he said that. With that one, the version. So kind of rephrasing for the recording, that so Alex, you spoke with Alexei, the author, and so he had a new version where he replaced some things in the architecture with Mamba, and when doing that, actually using the multi-level encoding, he got better results. The conversion is faster. Mm-hmm. Yeah, I mean, that's the criterion. Training time, maybe in that case, yeah, you will go for it. Yeah, I mean, it's totally valid. I guess it's an alternative, and perhaps there are still a few more years until we converge to one or the other option. Maybe this is just, you deviate. I guess that happens with research a lot, right? Like, you start this, and then you realize, no, that was not a good idea. Let's get back to this. That happens. So, yeah. Okay. So, getting back into the end-to-end neural diarization, and maybe now describing a bit more the architectures. So kind of what's written there and the diagram there is kind of what we saw before. Just I wanted to show you here the type of architectures that were used in 2019. Well, there were just BLSTMs as encoder. That was it. Once you process that with your encoder, you have some linear and sigmoid to classify and get kind of the probabilities of the activities out there. They even had some deep clustering loss. So you would also, each of the per frame embeddings there, cluster them into silence, speaker 1, speaker 2, or both of them. But then eventually they dropped that. So I guess this was something that, yeah, they tried it. It seemed to work here, but then in future works, they dropped it, so probably not so useful. That happens quite often. Now, these models are fine when you have a limited set of speakers, like for example 2. But what happens when you have more? Like a priori, in diarization, we might have an unknown number of speakers. So the first work that appeared in this direction was this approach based on the speaker-wise chain rule. And the idea is, well, you have your model, and you will decode one speaker at a time. So they will have an LSTM-based decoder that will produce the probabilities that will give you the activities for the first speaker. And then you will use this as input also to your model, together with the features, and then you will decode the activity of the second one. And you will continue like this until eventually, at some point, well, the decoding doesn't give you any more speech, so that's time to stop, and that way you decode potentially an unknown number of speakers. This, however, was not so successful. It didn't continue, and kind of in parallel, from the same authors, they proposed these encoder-decoder attractors, where the idea is somewhat different. So you have your audio features. You will have your encoder, which eventually by then it had already transformers. So the encoder incorporated attention, and you will have then some speaker embeddings, in this case every 100 milliseconds. And then they would pass that to an LSTM encoder. So you pass the whole sequence, and at the very end, you would have these hidden and context states that should have all the information that you had in your sequence. And from there, they would extract one attractor at a time. Basically, the input of the LSTM doesn't matter. It's like nothing. What they care is you would decode one representation, which we call attractor, that will represent one speaker. So that will represent speaker 1. Then you would do the same thing for second, third, and so on. How do you know how to stop? Well, you will classify each of the attractors. So you take A1, and you will pass it through this linear and sigmoid that will give you the probability that that speaker is active or that it's valid. So when you train this model, you will show sometimes 2 speakers, and in that case, you will be showing the model 1, 1, 0. So that's a marker for stop decoding. Sometimes you will show sequences with 3 speakers, so you'll have 1, 1, 1, 0, and so on. So you vary that, and the model eventually learns that it has to classify until some of them are active, and at some point I will find, or not active, but valid, and at some point I will find one which is not valid, and I will stop decoding. So that's kind of the scheme for finding the number of speakers. You have the attractors, you have the embeddings. Now we need to know which speakers are active at which frames. So what they do is dot product between each frame embedding and each attractor. Dot product, if 2 embeddings point into similar directions in space, that will give you a high value. So when you pass it through sigmoid function, that will give you kind of high probability. So if they point to similar direction, that means this speaker was active at this moment. If they point to different directions, that will give you low value, so probability will be rather low. And that's basically how you get your matrix with the diarization results that then you will use for training. So this way, this model handles this variable number of speakers. There have been many different proposals since then, and kind of one of the main things was, let's get rid of that LSTM part. So as you see, there have been quite a few different varieties of incorporating attention to decode the attractors. I will not cover them. Each one has its own different little differences here and there. But eventually, with all of them, you can improve the results. And this is just to name a few. There have been quite many works, not only in terms of the attractors, but in trying to improve in terms of the encoder, different parts of the model. All right, so I will now move to one of the characteristics of end-to-end models, which is training data, right? So we mentioned that for some tasks, we have plenty of data, so you can train neural networks very easily. That's not the case for diarization. Even if you put together many public data sets that have manual annotations, you will be in the order of hundreds of hours, which Yeah, it's not so little, but it's not a vast amount to train several million parameters models. Those kind of models require lots of training data. So the compromise solution has been, since the very beginning of this end-to-end neural diarization, to generate synthetic data and train the models that way. So the pipeline following this approach is you first train your model with 2 speakers per recording. It learns some notion of speech, how to encode it. Then you adapt it to more speakers, still simulated data. And then maybe at the end you have a few hours of real data. So you just fine-tune it, low learning rate, kind of to adapt some things here and there and get the best performance that you can. So in that sense, the original work of end-to-end neural diarization proposed these simulated mixtures, which is very similar to what is done for source separation, another task where you will basically mix, like you have recordings of 2 different speakers, you mix them, and the model needs to separate them. So they did something very similar, just adding some turns here and there. And the idea was, well, in telephone recordings, you usually have, if it's recorded in a certain way, you have one speaker in one of the channels and like kind of stereo, and in the other channel, you have the other speaker. So probably and I mean not probably, but for these speaker recognition evaluations, over the years, they have collected thousands of hours of telephone speech. Maybe it doesn't have, it doesn't have diarization labels, that's for sure, but it does have identities. So you know which speaker is on which side. So across recordings, you know this is the same speaker here and here, so I know that. So maybe I can use this to generate synthetic data. So you need to insert pauses. You can, I mean, a priori, you can take this recording of conversation A of speaker 1 with speaker 2 and conversation B of speaker 1 with speaker 3. So speaker 1 is the same, so perhaps you will not mix those, but you can take speaker 1 from here with speaker 3 from here, and you put those together. Well, one will be speaking at a certain time, the other one will be speaking at different times because there were 2 separate conversations. That would probably not match reality so well. They tried to improve that. So they would say, well, if we run voice activity detection, we can get some weak supervision, so it's not perfect, but we get some notion of the segments of speech in that side of the conversation. We get the segments. We can then randomly sample, let's say, 20 to 40 of these segments, and then we need to insert some pauses in between. So what I did was, let's use an exponential distribution. You can play with these beta hyperparameters so that you make, like on average, shorter or longer pauses. And then you have segment pause, and so on. If you repeat the same thing for another speaker, now you will have these 2 guys. You can sum these 2 sides of the conversation, maybe add some background noise. The same way here, maybe you reverberate the signal to kind of do some data augmentation, improve let's say, the overall training of your model. Same thing here, some background noise, and that's your simulated mixture. So that's kind of reasonable. There are some issues, though, because here, when you have only 2 speakers, maybe it's okay to do these defined turns and that's okay. If you want to train a model for 5 speakers that can handle 5 speakers, you will repeat this independently for each of the speakers. And when you sum 5 different independently defined turns for the different speakers, you will end up probably with a lot of overlap, much more than what you would see normally in real conversations. And you could argue, well, I can play with beta, extend it, so that now there is a bit more space in between them. But that space will tend to be similar for all of them. And now you will have maybe a lot of silence, not so much overlap, but maybe not so many single speaker turns. So it will not match a real conversation so well. So some of the work we did was to, okay, let's try to improve this and see if we can actually improve the quality of our model, because we improved the quality of our simulated training data. So we said, instead of defining the turns independently, let's do that collaboratively. So we have the size of the conversations as before, the telephone conversations. We run VID, we get the segments. But then what we do here is we randomly interleave the segments. So we still keep the order of green 1, green 2, green 3, red 1, 2, so on. We keep that. we interleave them, but now we define the pauses or overlaps based on statistics from real conversations. So if you have 2 consecutive segments from the same speaker, well, they will not overlap, that cannot happen, but what's a reasonable pause to insert in there? So we have the distribution, basically the values in a real conversation. We can just pick one of them, sample, and that's what we will use. Now, if we have 2 different segments, like different speakers, segments here, like green and red, well, here they can overlap, so there is a probability of them overlapping or having a pause in between. So same thing, we would sample, and that way create these simulated mixtures. Again, we also add some background noise and these kind of things to improve the quality, but this way, this is much more friendly when now you have many more than 2 speakers, because, well, you still have some probabilities of overlaps, but the chances of overlapping 3 more, 5 speakers at the same time is not as high as before. And just to get you an idea of how much this can improve, these are results on Colholm, which is a very popular telephone data set for diarization. And we have the different steps. If you train only on 2 speakers, then when you adapt to 1 to 4, so the model can learn that the number of speakers can change. And then finally, some fine-tuning on development data, like in domain. And we have on top simulated mixtures and then the simulated conversations we proposed. And you can see the DRs, so all these numbers are in terms of DR. You can see that even the model just can handle 2 speakers, even though our test set has more, it's not only 2 speakers, but that already brings the DR much lower, like almost 8 points down. And when you have the results for the model adapted so they can find variable number of speakers, that lowers even more, to the point that now the fine-tuning step, which was crucial, is actually not that relevant in this case. So just by improving the quality of the simulated data, we were able to improve quite a lot. This is maybe not so crucial, or maybe it's crucial everywhere, but I would say the differences become larger as you tend to have more speakers, because that's where the simulated mixtures become less accurate. And this was not the only way. Kind of contemporarily, there was another approach that used something similar, so also some kind of statistics about the turns. In their case, they would analyze the different types of turns that you can have in a conversation. So there is kind of a catalog of, these are the type of ways of 2 segments from different speakers to happen in a conversation. So they would like propose 2 options. One of them, the probability for each of the classes over there, estimated on real data, or a more complex one where you have this Markov. Okay, so depending on where I am, I decide what will be the next type of turn. So they would have this matrix also estimated the probabilities on real data. But in their case, this kind of maybe a bit more sophisticated way of estimating the statistics in comparison to what we proposed didn't bring so much gain in comparison to this concatenate sum that's basically the simulated mixtures that I was commenting in the previous slide. So there have been alternatives, but I would say that we are not done yet, because these type of approaches, in our experience, the simulated conversations worked quite well on telephone, but when you wanted to do well on other types of acoustic conditions, that was not that great. And something that we even discussed in 21 when we were doing this was, okay, it would be quite nice if we could generate a transcript, or maybe even take the transcript, like the real one from a conversation, an existent one, and then use TTS to generate the size of the conversation. And now you have, maybe you have a set of many different voice prints, like speaker voices. You can condition your TTS, and now you have all these different combinations. And no, that could be nice. Like this was many years ago, or like in 21, we thought, yeah, it would be nice. We never got to it. But nowadays, that generative models are way better, not only in text, it's obvious, but even in speech, generating voices has become quite like much better. It has improved a lot. Eventually, generating good quality audio probably will be better, but it's still kind of open. At least for diarization, it hasn't been like so explored as these other works. So that's kind of something maybe worth exploring. The thing is, can you generate any kind of audio with the same quality? Well, I guess that's definitely an open problem. Like if you want to generate meetings and restaurant and telephone and whatnot, that's not there yet. So just to kind of get to a comparison between the modular and the end-to-end systems, this is with some of the models that we talked about before. So I will be showing results here with 3 different data sets with different characteristics. So I mentioned call home, which are telephone recordings, the results that we were seeing before. So 2 to 6 speakers per conversation. There is this AI Shell 4, which are meetings. So this is a microphone array, so it's kind of far field, the collection of the recordings. And here you have more speakers, 5 to 7. And there's this Mixer 6, which contains interviews and telephone, but it's always 2 speakers. And we'll see now the comparison between a modular, one possible modular system, so it's based on VBX, and it includes overlap detection. And then we have Diaper, which is one variant of end-to-end model that we worked on. And we have the results in terms of DR and then mean speaker counting error, which basically tells you how accurate is the model in finding the right number of speakers. So both of them, lower is better. And you can see that for this particular scenario with telephone, both of them perform very similarly. There are not really very large differences. But when you go to this far field and many speakers, the modular system is much better. But at the same time, if you go to this other scenario where you have only 2 speakers, actually the end-to-end model is much better. Like maybe not in terms of number of speakers, this is probably just one file in the whole collection, so this is maybe the same. But here you see by handling better the overlap, it can reduce the error substantially. So analyzing a bit more in detail what happens in call home, depending on the number of speakers in the conversations, you get very clear trends. For fewer speakers, 2 or 3, Diaper is way better, or at least better, depending on the case, but it has some advantage. Once you go to more speakers, that's where the modular system starts to perform better. So there are these things that, well, each one of them has pros and cons. We commented on the ones for modular systems with end-to-end models where now you have a unified objective, so you train for diarization. It's also a single system, which is convenient, like you don't need to run all these different steps. And the overlap is handled naturally and kind of putting focus on it, so it's not just like as a post-processing. Difficulties, well, training is not that easy. We commented, you need lots of data. You don't have so much, so you need to maybe generate it or start doing other things. These models struggle with many speakers, as we saw in the results, and they eventually can be biased to the type of training data that you use. So generating simulated data with telephone is kind of easy. If you want to put, we tried it, generating simulated conversations with recordings from Voxelab. Voxelab is recorded on many different acoustic environments. And that means that somebody has background noise of certain type, another recording has different. When you put them together, there are certain mismatches that the model learns. So if you evaluate it on that kind of fake data, it works well, but that doesn't translate into better performance for the real scenario, which is the one that you want to handle. So there are still these issues. So we commented that there were modular systems, there were end-to-end systems. And then now there are these hybrid systems, let's say, which combine both things. So one of them that we could call hybrid in some way is TSVAD, Target Speaker Voice Activity Detection, that came in the context of the Chime Challenge in 2020. And the idea there was, well, you would first run some diarization system, initial, maybe not perfect, and probably it wouldn't handle overlap, so it would be kind of a modular system. And then you would try to handle the overlap or refine the outputs with something need something a bit more end-to-end. So the idea is, well, now you have these diarization outputs. You have your speakers. For example, segments 1 and 2 correspond to the red. Then 3 and 4 have the same label, speaker 2 in green, and then 5. So you can extract one speaker embedding for each one of those. And then you extract that, so they should represent the speakers, all of them in this conversation. This also happened in the context of this chime challenge where you have had always 4 speakers. So you always knew, okay, there are 4, so I will extract 4 representations and I will have them there. And then you combine frames. So they are like coming from a different feature extractor. You will have per frames with, I don't know, very nice granularity. You will put them together with your speaker embedding and with this frame speaker detection, just now discussing in like high level, you would get now the activities for them. And then you would get the activities for the other one. And then finally for the third one. So independently you would run for each one of them and then just combine this information. So as you see now we can handle overlap because at some point there were 2 of them active. Just for you to get an idea of, in 2020, what was the architecture in that case, well, the speaker embeddings were I-vectors. So I mentioned that, oh, I-vectors were an old thing. Well, back then, they managed to make it work with I-vectors, and it took a while until X-vectors could be plugged in this kind of architecture, and they worked better. So they used that as speaker embeddings. You see here that the way of deciding on the activities is separated into 2 parts. So there is first this BLSTM that will give you some per speaker representation, and then there would be this combination to produce the final outputs. And the features that they would be obtaining together for this, how I called it, I forgot, the frame speaker detection, which is kind of this block over here. The features that they would use in terms of acoustic features was MFCC through a few layers of convolution network. So this was in 2020, and there have been quite a few works trying to extend this, improving it. Just to put here one of them as an example, as we know, yeah, transformers started taking over everything, and replacing those BLSTMs was one of those options. So, for example, in this work, they replaced those BLSTMs by transformers, but they also had an alternative version to handle variable number of speakers, where they combine this idea of like TSVAD-like detection of activities with the notion of attractors that we discussed before in the end-to-end neural diarization with encoder-decoder attractors. So they will have these LSTMs encoder-decoder, and you get the attractors, and that's what you use for finding the activities. So this is one possible approach, and there have been many works like around these ideas. Of course, I will not cover everything, so it's just one example. And then we move to the end-to-end neural diarization with vector clustering, which is nowadays probably the most popular, best approach. Like if you can combine these 2 things, I guess that's maybe the way to put it. So if you want to get state-of-the-art results, you would probably go for something like this nowadays. If you don't really care about developing better diarization, there is a solution you can run. And the idea here is, well, you want to get the best of both worlds, as they named it in one of the papers. And you would run end-to-end diarization in relatively short segments of speech. So you can see here there were 2 speakers. So you run your neural network end-to-end. You get activities, and you also get a speaker embedding that will represent that speaker. You do the same thing in another chunk. So now you get activities for the green and the blue. And then there is one part which is, well, they were run independently, these. We need to put that information together because maybe we have several minutes of recording and this is just a few seconds. So then, using these speaker embeddings, they would do some clustering. So then they realize that, oh, this embedding and this embedding are quite close to each other, so they must belong to the same speaker. And then you just stitch based on those. You just stitch the activities that you detected with the end-to-end part. And just to get you an idea, I don't know if all of you have been already doing research or you are more new to it, but it happens quite often with research that you just don't come up with the idea and it works perfectly and yeah, you dominate the world. No, usually it's kind of work, several months, probably iterations and improving. And this shows it quite nicely. Like you have 3 iterations until eventually they go to this kind of version and kind of stable in some way. And this was actually not the last one. Just to name the last iteration of this combined also with the clustering that we saw before, where they introduced the hidden Markov model in the same way that we saw it before for just doing diarization with speaker embeddings. Now the idea of extending it so that each of the states actually represents either one speaker or the overlap between 2. So kind of these extensions that coming from modular systems, these ideas can still be put together with end-to-end models. And this is kind of where we are going with this. However, nowadays, probably the main reason for this work to be so, or this approach to be so popular is that Pianot implements this type of model, or slight variation, but very, very similar. And the idea, and this figure is, for example, taken from those papers, but this idea is, well, you run your end-to-end on sliding windows, so you have this local end-to-end. And the thing is, the assumption, if you run your diarization on short segments of speech, maybe up to 10 seconds, you are probably quite safe in assuming that there will be not many, maybe 3 or up to 4 speakers in 10 seconds. Maybe in some cases you can extend it, but usually you can put a safe upper bound on that and run it on those few seconds. You do that on a sliding window. For each one now you will have some activities, and for each of the speakers that you find in each of these segments, you extract some speaker embeddings. And then you cluster them, just like we saw in the previous slide. You stitch them, put them together, and that's how you get the outputs. Just in this slide to show you kind of the versatility of this approach. First of all, well, we have 2 parts now, the speaker embedding and the end-to-end. In the end-to-end, if I'm not mistaken, I don't know if it's already been updated, the Pianot version. Maybe it's already not. This is not the latest version, but for quite some time, or at least when these papers appear, at least the first one, the idea is they would have as encoder a syncnet, which you can think of it as kind of some convolution-like way of extracting features directly from the waveform. And then they would have some VLSTMs, and then the linear plus softmax to classify. Originally, there was not even the power set multiclass, then that was incorporated. So some of the things that we discussed before appear together with this. And I was saying kind of beauty of this that we saw before for the modular systems is the chance of replacing things. So this speaker embedding part, well, I think at the beginning it was a kappa TDNN from the speech pairing implementation. Then it was replaced, I guess nowadays is the WeSpeaker models that are performing quite well. And that's something that, well, as long as they keep getting better, you can very easily replace that. And as long as you have the code to extract the embeddings and then run the clustering on top of that, you're good. And it's a kind of easy way of improving that. I will comment now on some work done mainly by Zhang here on improving. It hasn't been the only work. There have been different works trying to improve the encoder part. But with his work, he got quite strong results, so I wanted to incorporate it here. And it also touches on something which is self-supervised features, which Olda covered quite extensively yesterday in his presentation. So this is kind of the architecture that was there when he started working, and the idea was, well, let's update this encoder so that we can get better performance there. So one of the things is using WaveLM. So as you saw yesterday in Olda's presentation, these WaveLM or Wave2Vec2 and these kind of models usually have several layers of transformers. So the usual way of utilizing them is you take the outputs of each one of those because they might have information relevant for different things, and you give some weight, you learn that weight, and you combine those outputs eventually with some linear layer, and that's kind of the first part of the encoder. And then he replaced those VLSTMs by conformer layers, which is, let's say, don't quote me on this, but kind of an extension of transformers better suited for speech. Because in speech, usually the short time context is quite relevant, so convolutions are very good at that. They have a very strong bias in the way they model things, unlike transformers that are more flexible, but they give you the chance of seeing the whole picture, let's say, in your input. So this kind of combines both things. It adds a bit of bias, local bias, and at the same time it has the flexibility of the transformer. And that eventually provided quite some nice gains. And with this work, Zhang showed basically some nice improvements. So we have at the very top the results published before. Then this baseline where he used the SyncNet, and if I'm not mistaken, the replacement of the conformer where there was already some improvement. No, this one with the FBank, that would be with the conformer. And then adding the WaveLM frozen or updated, you can see that you can still squeeze some more. And over these data sets, which are quite popular nowadays, all of them are meetings. So you have lots of overlap. Quite some improvement over that public recipe. His repository is also public, so people can run it. One of the issues at this point is, well, you had kind of a lightweight encoder. Now you have huge WaveLM, or I mean, huge. I guess what's huge nowadays is being challenged month to month. Like 1 billion parameters now is like, what? It's tiny, right? Depending on the task. But here, of course, this means quite an increase in the number of parameters. So kind of the follow-up of that was, well, he said, let's try to improve that. So let's prune the WaveLM model. So let's not keep everything. Let's just keep the things that are relevant for the task at hand. And that's what he did. So this paper will appear soon in Interspeech, so I guess he will be presenting it, I assume. And so the comparisons are quite nice because now, so there are the results with the base plus and the large version. Changes basically the number of parameters. You can see like close to 100 to a bit more than 315. And with this sparsity, basically, the model is trained to basically realize these parameters are not so relevant, so they get kind of removed from the final model. And you can control how much you want to remove. So that's the level of sparsity. So 80% sparsity means you keep only 20% of what you had originally. And that's quite nice because, well, you reduce the number of parameters, but maybe more relevant is you have a nice speed up. You see here, like for 80%, 4 times faster, but pretty much the same performance. Like in the macro evaluation, like across like average for the different sets, it's pretty much the same. And for the large version, is basically the same. But a nice speed up with respect to the original model, just with the WaveLM. You can say, well, maybe I want a bit better, a bit faster, so you can increase a bit more the sparsity with a little hit in the performance. So this is a way to show, I mean, this is not the only way of including self-supervised features. There have been other approaches, but just to include something that is kind of being developed right now on top of the Pianot pipeline, which is nowadays probably the most popular diarization toolkit. So I guess if anyone wants to try, probably that's a safe bet. This is not the only trend. Also in combination with ASR, doing diarization, so basically transcriptions with speaker labels, there have been quite a few works on this. Maybe more historically, or what one of the approaches that even nowadays can be done is you run both diarization and your ASR independently, and then you put those together. So you get your segmentation with diarization, you get your transcription, and you also get from your model some timestamps. So then you need to align those and say, well, from here to here, that matches this segment, and you put that together, and then you can have nicely colored words. That's not the only option. Another option is you do first diarization, you get your segments, and now on each of these separate segments that you get, you run transcription. So this can have the disadvantage that perhaps, well, what happens before and after could be relevant for transcription, and perhaps you're kind of missing that. But it's a maybe cleaner way, and you don't need to process extra, especially if you have lots of silence, you don't need to run inference on that. So that could be like a transcription inference on that, I mean, which it can be an advantage. Or you could even add in the middle source separation. Here my example is not the best, but I was a bit too lazy, I didn't manage to update it. This makes sense mainly when you have overlaps between speakers. So here in this example, they are all nicely separated, but imagine that you have two of them, one on top of each other. Source separation, what does is it will give you one recording for one speaker, another recording for the other one. So if they eventually overlap, well, hopefully, if the separation works well, you will have rather clean segments of speech in each part, and then when you run the transcription in each of the channels independently, you can recover and basically get the nice transcription for the overlap part. This is tough, like source separation is not an easy task. It's kind of similar to diarization in many ways, but you go one step further because you need to generate the audios that correspond to each of the speakers. There are other approaches of combining ASR with diarization, and that's basically including speaker terms, and that's this comes with this serialized output training, where basically when you do transcription, you have your words. If now I have different speakers, what they do is they include speaker change tokens in between, so that marks that the turn of the speaker finished and the turn of the second speaker or the other speaker starts. And they train the model to output not only the ASR tokens, but also these speaker change tokens, so that then when you run inference, doesn't have to be streaming. I mean, they also worked on doing it streaming, but batch will be the same. Basically, you will be outputting your words. And for example, at the beginning, you assume, well, I will start with speaker one because, I mean, this was said by somebody. So speaker one, whenever I find a change token, I will now switch to speaker two, and whatever is output by this, like transcription, this will correspond to the second speaker, see a change, get back to speaker one, and so on. This is kind of easy when you have, or I mean, easy. The switch between one and the other is kind of flipping because you only have two. If you have more, it becomes a bit trickier, and your change tokens have to also give you cues about which speaker was there and so on, but the idea is somewhat similar to this. And then similar in some way is, but maybe more related to the modular systems, is the notion of this turn to diarize, where you do the same thing. So you have your words with change tokens, but this is a bit more friendly for the case of more speakers, because what they do is also incorporate a speaker encoder. So in between change tokens, so that means this part, independently this part, and then this part, they would extract a D vector, so some neural network-based representation over that segment, and then do some clustering for those. So that if, let's say, if you have more than several speakers, this eventually, with the clustering, gives you the power to label them correctly. And then, I think Alex left, yeah. But there is also, I don't know actually, guys, how you pronounce it, but I would say decal. Anyway, this is work quite recent, and for those of you that are interested in this, there will be more on Tuesday next week, so that's kind of the advertisement for you. And basically the idea is you want to condition the transcription on the diarization. So you get masks, which can be binary, but it can also be the probabilities, and that enriches eventually the possibilities of the model, because now you incorporate the decisions or the probabilities into the encoder of the model. So the model can handle that, and somehow they are exploring different options, incorporate that information to improve the transcription and already give you the better outputs that take into account the speakers. And then, of course, because nowadays LLMs are everywhere. There have been recently some works of trying to incorporate large language models as well for error correction. This is not the only work. There have been a few, usually from the large companies that had these models available for them. But basically, I mentioned at the beginning that if we run independently the diarization and the transcription, now we need to put them together, and there could be some misalignments here and there. So what they did is, well, let's prompt a model. They eventually fine-tune, but basically the idea is, this is after I do this fusion or combination of the transcriptions and diarization annotations, given the timestamps, there might be some errors. Like, for example, good morning, Patrick, how are you? Good, good. How are you, Tom? Pretty. I mean, we read that, and clearly that's not speaker one and speaker two. There were some errors. So the idea is basically correct these kind of errors in how the words were assigned. And it kind of works up to a certain extent. Now the thing is, this is a nice proof of concept, I would say, from a perspective of application. If you want to run fast, this is very expensive. Like running an LLM is way more expensive than running the speech-based models. So that's something to take into account, unless in the future LLMs suddenly become speed of light. Like this is kind of nice, but expensive. And so to recap, kind of over the whole, like we are coming to an end. So to recap the presentation, well, we discussed what diarization is, what are the challenges that are there. We discussed the modular systems, end-to-end, hybrid, and then kind of the connect, like these recent trends combining diarization and ASR. So some conclusions that kind of to summarize. Well, we know clustering-based approaches, modular systems have been around for a long time. The improvements on speaker embeddings have been huge over the years, and that improved the models a lot. But then it got to a point that overlaps became the main problem. Besides, running these type of pipelines is somewhat tricky. So end-to-end models in some way come to help in connection with the overlap, and they can do that nicely. They just provide a solution with a single model, so that's also pretty nice. But they also have their problems. They are not perfect. They need large amounts of training data. So one option is, well, generate or collect, which will be very expensive, data with annotations. They also struggle with many speakers, so that's also something to take into account. An alternative to the large amounts of training data is, well, leveraging other types of supervision, like this cheaper supervision, like labels, like speaker labels for speaker recognition. That's an option. But also using self-supervised features, models, incorporate them as we saw examples here, but it's not the only case. That could be another way of trying to avoid having to generate all that training data, which is not the matter of generating it, but also consuming it. So training on thousands and thousands of hours is not cheap. That's related to this other point about memory consumption. We know that the attention mechanism can be expensive when you have very long recordings. So in that sense, if you want to have a single end-to-end model that handles the whole recording and you have several minutes, that will be expensive. It will take quite a lot of memory. So in that sense, or in that direction, end-to-end models with vector clustering tackle that, because you can run, even though it might be expensive to run end-to-end, it's over a few seconds, so you can do that. And then you still leverage the improvements in vector clustering to provide the final diarization. And this covers the issue of end-to-end models not being so good with many speakers, because end-to-end in a few seconds can handle just few speakers pretty well, and then the clustering, which is good on many speakers, can take over. That's it. I guess we do still have some time for questions. So, yeah.
Thanks, Felix. Any questions?
I might have one question.
Maybe take the mic so that the people that are watching the front streaming can also enjoy the question.
Uh, I'm just wondering because you show some that in the, let's say, the first kind of models, you have some, let's say, channel-dependent performance depending on meetings or maybe if you go to restaurants recordings. So my question here is, there is any contribution for by using the self-supervised models in those channel-dependent performance?
So I would say that maybe it was more like end-to-end models struggle more with that variety in comparison to modular systems, but modular systems will also struggle. So not just like kind of rephrasing the question a bit, yeah, so the problem is the models become biased to whatever they are trained to I don't know, handle. Self-supervised models, if they are trained on rich and vast data and they cover the different scenarios, probably that will be a good thing, like a good addition. For end-to-end models, mainly because that's maybe where they struggle more. Modular systems are a bit more robust to that, but they could still work better. Like yesterday, Olga was commenting on the speaker embedding extraction, right? And leveraging self-supervised models. Maybe that's actually a better way of handling with the same model different types of audio. So that could be. Yeah.
Thank you.
In the beginning, you mentioned these short segments, like, for example, the back channels. Do you have maybe some recommendations how to handle them in modular systems? And second to that, how do end-to-end systems handle them? Are they better than modular systems in handling those short segments or not?
Right, so end-to-end systems are better at them. I don't think anybody, as far as I am aware, has analyzed them in particular to say, okay, how exactly do they perform with the back channels, which could be done because there are the labels, right? So you need to, let's say, compare what's the performance on those versus the rest. So that could be a nice thing to do, to get an idea of how poor or good they are. I guess end-to-end models will be definitely better than the modular ones on that because, well, they will handle overlap better. And then kind of the second part of the question was more on?
So in modular systems, how you would recommend to handle those short segments? Like, for example...
How to do it in that case?
Yeah.
The thing is, I mean, you rely on finding the overlap, right? And the solution, this handling, or like I would say the detection is the main problem. And finding them is not so easy, mainly because it's also the problem of detection when you have a very imbalanced problem. Overlap detection is quite imbalanced. Even in the cases that you have high levels of overlap, maybe you are talking about 20%, about. And when you have 20 versus 80%, finding the overlap is kind of, yeah, it's an imbalanced problem, so it's hard. And we are talking about the back channels, which are the minority and the toughest of them all. So you could say, well, maybe if I train with more of those, like I create artificially, maybe some of them, that's something that people have tried, but I guess there are limits onto how much that can get. And honestly, I haven't really thought much further on that, but yeah, how to improve overlap detection for modular systems, that's tough. I actually tried that kind of at the beginning of the PhD, and it didn't lead very, very far. So it was, yeah, okay, tough.
Thanks.
How widely used is a post-processing step for hybrid models, not only with LLMs, but with maybe other heuristics or steps?
In practice, let's say, I don't know, companies doing diarization, probably not. I guess the solutions will nowadays tend to be more towards either end-to-end models, if you want to handle that, or if it's more like clustering, probably they will not have overlap. I mean, I don't know what everyone is doing, but that's my assumption. In terms of publications and baselines and so on, I would say it's not that common to have these. So fewer works would include this post-processing. Mainly because of what I was saying, yeah, overlap is maybe where you want to get the most but it's tough to get some improvement. So kind of doesn't add that much.
Thank you.
Yeah, good day. Is there some context where modular system still prevails?
Is there any, sorry?
Is there any context where modular system still prevails and like only 6 years ago it was the best system, how it goes now?
So when you have many speakers, I would say in many cases probably will be still quite good as long as you don't have so much overlap. If you start to have overlap, probably something like end-to-end with clustering, with vector clustering, will already do equally or better. So maybe it also depends on the application. Like in a real application, in certain cases, maybe, yeah, you don't really have so much overlap, and maybe it's faster to run or like easier if you already have the technology, so people still use the clustering. So in that case, it prevails, not necessarily because it's better, but kind of convenience.
Okay, and as I understand, main feature of vector clustering is consuming less resources like memory and producing relatively good results.
Which one? I missed the beginning. Which type?
Vector clustering?
The vector clustering that consumes like less resources. Depending on how you run it, probably yes, or you can at least run it faster if you parallelize things. That with the end-to-end model, there is certain limit on the parallelization. With end-to-end and clustering, you can parallelize certain things because each chunk can be run in parallel. But yeah, I don't think we have a very like thorough comparison on which one you should go for. Maybe I'm missing something. Yeah.
Okay, thanks.
Thank you very much. I had actually two questions for this. So my first one is on some of the slides at the end, you were showing the coding conventions basically for this speaker attributed speech with diarization. Mm-hmm. So either you mark the speaker 1, speaker 2, which is clear and obvious for me, or you had these CC codes like the speaker change. I was frankly always intrigued by this speaker change because this is this one. I have no idea who the hell can use that actually, because if you do like one error in the speaker attribution, then you have like one line incorrect. But if you do an error in speaker change, then you get the rest of the conversation swapped. So can you give us a clue, like who is interested in this? Is it some like media companies, or who might even want like this speaker change marks?
I agree with you that with this flipping version, once you make one mistake there, it will flip everything. And unless you make another mistake to correct it, you will be doomed. Yeah, that's true. In that sense, I think this one handles this situation a bit better because it still has the change tokens, but it relies on embeddings. Mm-hmm. So you still extract an embedding in the turn. You can have a mistake there, but you cannot recover from that error if the change token is in a wrong place, but at least it doesn't kill the whole output because you would still rely on the clustering to align things properly. So I think this is more of, the other one is maybe more of a proof of concept, so to speak, like it works to a certain extent, I guess, but it has these problems. This solves that by let's say, rely on the clustering.
Okay. Thank you. And my second question was in one of these newer diarization challenges, I don't remember which one it is. There were like these classical cases like isolated speakers, speaker overlap, but then there were these like sermons or masses in the church where there is lots of people, like maybe 50 people saying the same thing, like the prayers at the same time. And we were discussing, I think, with the speech guys at lunch, and we just couldn't agree if this is like a single speaker, speaker overlap, or some multi-speaker. So what is your take on this?
So my take on it is you train your models with certain labels. So you need to think, like you need to define your problem and set like the protocol for it. Like what do you expect my technology to do? So it's a matter of, like, not of the technology at all, but rather how do you define that. I personally wouldn't care about diarizing that part. Probably some other label like everyone,
Yes.
or something like that would make sense, or maybe it's not everyone, but many speakers. I don't know, so something along those lines probably should be enough.
I mean, I think like for the classical business scenarios or research scenarios, this is completely out, like, and we might think like, why to even think about that? But then I thought you have these Christian channels on the TV, and they probably want to provide some transcription for the hearing impaired people, and they just want to know when everyone is praying, so might have some sense. Okay, thank you. Other questions? Yeah.
I think you had mentioned that the end-to-end models were maybe not working as well when there's more speakers, like 4, 5, or 6 speakers. And one of the things you mentioned was with the simulated conversations that maybe it wasn't as realistic. So is your suggestion that there should be an increased amount of training data for those, I guess, situations, or that the simulated conversations need to be more realistic to 4, 5, or 6 speakers?
So you mean like increasing the amount of data that you have with more speakers, or improving the quality?
No.
Maybe a bit of both. So I mean, I explored this like increasing the number of speakers, and I trained with up to 10 speakers, like in the experiments I did with Diaper. And I didn't get to explore, let's say, what happens if I increase a certain particular quantity. I did, with the previous model we were using, something where I would follow the same distribution as in a real data set in terms of number of speakers per conversation. It was not necessarily better, but maybe the model couldn't take advantage of that. And then I didn't repeat it with, let's say, a more powerful model. Maybe if you put a bit more bias towards the type of scenarios that you expect, that will work better. The thing is, it's quite expensive to run the experiments, and you need to generate the training data, put it together, and train for quite a while on these several thousand hours of speech. So that makes it a bit tricky to get a good idea of how it works. But then definitely improving the quality, I assume that will help. I don't know if necessarily for more speakers, but maybe in general, like for any kind, if you have better simulated data. Sanjeev? Yeah. I was expecting, I didn't know exactly when it was going to come. But.
No, it's all right. So several questions, though. One of them is, TSVAD and those kinds of things. They took the diarization problem and turned it into like a speaker tracking problem, right? You said, okay, I have a vector for my speaker. I just want to track the speaker throughout the conversation. So are there any tricks from the old speaker tracking literature that we missed or haven't tried in this case? Because to me, that sounds like an interesting way of approaching the problem, partly because this thing with back channels, I don't see any other hope of identifying that speaker who says, unless I have a model for that speaker and I can say, okay, that sounds like my speaker. Because then you're looking at a closed class, there are 6 people in the room. It has to be one of them. So who's the one that said, So there's some hope. So do you know if there are any tricks in speaker tracking that we haven't tried, or did you try everything in your thesis?
Yeah, so I think this scenario where you have a limited set of speakers and then you can track them, at least in the literature, it hasn't been explored that much, right? At least recently, there are not so many works. Maybe before it was more popular, but it's specific scenarios where you would have this, like, as you said, meetings where these are the people that are here, and maybe you could even have enrollment, right? So beforehand, these are the people, or these are the attendees, and I have enrollments for all of them, so I need to just find when each one of them spoke. I agree with you, probably if you have that, then finding the back channels would be much easier. It's just, I guess, the way Diarization evolved over the past years has been more focused on this wide and ambitious framework where, you don't have that information. It would be nice, I think, if, let's say, for the academic community, if there was a data set that prepares this scenario. There have been many challenges. I think we didn't comment a lot on it, but after Die Hard, there were many more appearing in the last 5 years, which is nice. We're tackling different issues related to diarization, and well, I didn't include them, but one option could be this. I just don't know if there is enough push for it, like enough market or enough, interest. I guess there has to be certain requirement for it, and I don't know, I guess it will depend on that.
Right. Then the next question I had was going back to the question about modular versus end-to-end, right? What is the situation with very long recordings? If there's a speaker in the beginning and he or she shows up again in the end 45 minutes later, you're not going to diarize a 45-minute segment altogether with an end-to-end system, right? So, because what I'm thinking is in the modular system, especially if you're doing some kind of clustering, the length doesn't matter because in the end you have a bag. So do you have any sense for, this is asking the question again, are there situations in which modular might work better?
Well, in that situation, yes, if you only have end-to-end or modular, definitely. But given that nowadays with Pianot, has become quite easy to run an end-to-end with clustering.
Right, okay.
So that kind of scenario would probably be reasonably well handled.
Okay, yeah. So you're thinking that you use the best of both. You use end-to-end, but then you also use clustering across chunks.
Currently, yeah, I would say that's the best we can do.
Okay.
Maybe it will change. Hopefully in a few years, there are other things, yeah.
Okay. Another question I had was, how good are people at this problem? So if I listen to one of the AMI recordings, how well would I do as a diarizer?
I guess it depends a lot on how much time you will be willing to spend listening to the same recording.
Let's just say it's my annotation task. Somebody's paying me to do a good job. What's the human limit, basically?
I don't have I would be kind of saying a number, but for the sake of saying it, but it will be a few percent, probably.
Okay.
I don't know if we have, because for this you would need to analyze the inter-rater agreement, right? You need to have the same recording labeled by many people, and then how much do they agree or not, and that's basically defines this error. I expect it will be below 5%.
Below 5, you think? Okay.
That's my expectation. I don't have the numbers.
Okay.
But,
yeah. But I don't know that anybody has done any studies, have they? No.
Me neither, as far as, yeah.
Because I do remember one particular use case we had. Paula is one of our colleagues. She'll be here soon. She was looking at these collaborative project discussions. The data was collected by somebody in Singapore. And each meeting has anything from 4 to 6 participants. The thing is, they were all roughly the same age students, all from Singapore, working on similar things. And we had a hard time even figuring out how many people were there, let alone who was speaking when. There were lots of people who were so similar in demographics that we couldn't tell their voices apart. So it came down to the basic problem that humans are not good speaker recognizers anyway if you don't know the person. So there were lots of segments where we had no idea who was saying what. And unlike some of the AMI or other recordings where you have close talking microphone channels for each person, so you can actually listen to the separate channels to figure out who it is. This one only had distant microphones. So the ground truth was just awful. We couldn't do that.
Yeah, what you say is right. I don't know if all that yesterday commented on verification.
Yeah.
Machines are way better than humans, right, as you know.
Yeah.
And for this, well, given a constrained time, the machine will be better than humans, that's for sure. I think for humans, we can use other cues, perhaps. For example, if it's a language we understand, we will tend to use these cues to detect maybe, this clearly was a different person, which, given just the audio signal in a different language, maybe, as you say, if the voices are similar, that makes it trickier. There are these nuances, I guess, yeah.
Then, to elaborate more on Hansa's question about many people, right? So I agree with you that after about 2, 3, or 4, you should just say many, because you don't know how many people, probably doesn't even matter how many people there are, right? But then there is a situation I was thinking about where very often when you have some kind of large meetings, you do a voice vote. You say, all those in favor say aye, and you hear aye. And then all those against it say nay, and say nay. If I had just that, could I say which is majority? Could I say there are more ayes than nays?
I wouldn't trust Diarization on helping you on that. Yeah.
Okay, all right. No, there are all sorts of open questions. And Maciejewski, one of my colleagues, he actually is very interested in this problem of trying to figure out roughly how many people there are. Is it 5 or is it 20? Like, order of magnitude. And there's a corpus called the Santa Barbara corpus.
They were preparing it last year. Yeah.
And that corpus has many of these examples where there's some kind of sermon and something's going on. Yeah. 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 Right. I mean, for example, I'd like to know in a stadium how many people are shouting, whether it's 5,000 or 20,000. All right. More questions or more comments?
Over there. Yeah.
Hey, so I was wondering, to what extent do a diarization system use lexical cues or like linguistic cues? For example, like if you said that we were training end-to-end models on simulated data, right? So I mean, I was thinking like, okay, if you simulate data, you basically break the conversational structure of the data, right? Basically, the sentences or like the speaker-specific segments are just kind of random. So do you think that diarization models are using these cues to like do diarization? For example, like I'm expecting that there is some part of word that is going to be followed by another word from another speaker. Can use this information? Or do you think that these systems mainly use speaker-specific or voice-related information to do diarization? Because at that point, it basically boils down to a question, do we need to simulate better data? Or, like how basically to simulate data so that we can train these systems solely on simulated data, because getting real data and like tens of thousands of hours of real data is really challenging.
Yeah, so I guess currently the models focus more on this, as you said, like speaker acoustic information, probably not so much the content, but I mean, they are neural networks. Who knows what happens there in the parameters? And it could be that the language, what is said, is being somehow encoded, especially if you train with a, let's say, biased training set where you have always the same language. Perhaps that can be learned if your model is large enough. So there is this, I mean, I guess you already thought of this, but I would say that the current models are probably leaning more on the speaker acoustic cues. In the long run, I guess creating not only good, like nice sounding audio, but also that makes sense in terms of what is said, that will be needed to get to the last part. But also connected with one of the questions that I got in the break. Yeah, I guess that's maybe something to take care once you handle very well the acoustic part. Before that, maybe it doesn't make sense to focus on that. Everyone is hungry.
Yeah, well, I have maybe a quick one. There was, well, once upon a time, back in the 2000-something, we were in this European meeting projects like M4, AMI, AMIDA. There is still like this very known AMI data set. And there were some people that were theoretically or studying the conversational structure and the turn-taking and the roles of participants from some theoretical point of view and trying to define them like this is the leader of the conversation and there is like this kind of reaction, submissive, overruling, boss, whatever. I don't remember all that. But do you think this kind of information can somehow help the diarization, any of the systems like neural or component-wise, or is it completely like in the realms of theory and forgotten and overridden by the data? Because I mean, from the human point of view, if you have a conversation, there are people that have a very specific style of taking turns, like saying and then starting to speak. You know, someone can speak very politely because he reacts to some boss's speech. So is there any way to use this kind of information?
I guess it could, and I guess it's connected with the speaker tracking example from Sanjeev. Like, if you could enroll the speakers and you have this kind of information in your enrollment, probably you could know that. And of course, it would require that maybe you have previous meetings where you identify these kind of things. But if you know how somebody barges in the conversation, maybe that actually can be helpful for the model as well. I don't think, yeah, people have explored this, but yeah, I don't disregard it as crazy.
Thank you. Anything else? Well, not everyone's hungry, so let's clap and thank Fede again. And well, there is lunch, and we will resume at 1 p.m. as usual, and we will be here.